Hello and welcome back. This video will finish up section 6.2 on applications for the normal distribution. So let's just dive right in with another example. So here the weight of oranges is normally distributed with a mean of 140 grams and a standard deviation of 25 grams. So then if we're told that oranges between 100 grams and 200 grams are accepted by stores to be sold, so they're not too small and they're not too big, what percentage of oranges can be sold in the store? So first of all, again, drawing a picture I think is really helpful. If we think that all of these are going to be normally distributed, so we've got our nice little bell curve, and we've got our average, our mean of 140. And then down here we've got, say, 100, and up here we've got 200. Anything in between, all the oranges with weights between 100 and 200 grams can be sold in the store. So the question is, what percentage of oranges is that? Or if you were to pick any orange at random, what's the probability that it would be accepted to be sold? So again, what we'll do is we won't worry about that normal distribution as much, but we'll translate everything into the standard normal distribution. So with the standard normal distribution, we have an average of 0, and then we'll need to turn 100 into a z-score, and we'll need to turn 200 into another z-score to figure out exactly what those values are. So we have our first value of x is going to be 100. The mean is 140 grams. The standard deviation is 25. So when we look at this, if we need the z-score for the x value, for the leftmost value for 100, we'll take 100 minus the mean to see how far away from the mean we are, and we'll write that in terms of standard deviations. So 100 minus 40, well, that'll be negative 40 divided by 25, and this is going to be negative 1.6, as in 100 is 1.6 standard deviations below the mean, below because we have a negative z-score. 100 is less than 140. Whereas the other one, so we've done this x value, and now we do the other x value. So when x is 200, again our mean is going to be 140 again. Our standard deviation is still the same, it's 25, and then our z-score is now going to be how far away is 200 from the mean, and how many standard deviations is that? Well, this will be 60 divided by 25, which is 2.4. So this z-score is going to be 2.4. Now, we want to find the area in here. But if we come back to our calculator in StatCrunch, we can only look for the probability less than a value. If I let me put in something like this, we can find the probability less than a value, or we can find the probability greater than a value. But we can't look for the probability between two values. We will have to do the calculation ourselves. So when we look at this, what I will do is I'm going to split this into two regions. We have the region that we want to calculate, which is the region in between 100 and 200. But I'm going to add this little region over here, and I'm going to express the region in between 100 and 200 as the same as the area that's all less than 200, both the red and the blue regions. And what I'll do is I'll just subtract the blue region. I'll subtract the area to the left of 100. So let's look at the area to the left of 200, and 200 had a z-score of 2.4. So when I compute this, this is most values, so that's 0.9918. So let's write that down. So the value for this entire area is going to be 0.9918. So this includes a little bit extra, so I'm going to have to subtract off this little extra. Well, that corresponded to a z-score of negative 1.6. So if I look at the area to the left of negative 1.6, this is going to be 0.0547, I'll round that to 8. So the area of this little region here is going to be 0.05, I had already forgotten, 48. So if I want just the area of the red region, I'm going to have to take 0.9918 and I'll subtract 0.0548 to get 0.9370. Or in other words, 93.7% of oranges could be sold in stores. The other 6 or 7% would have to be used to make orange juice or something else. So the area of the red region is going to be the area of everything to the left of 200 minus the area to the left of 100. So you just take away that little extra tail to find the area between two values. And there's nothing wrong with doing this on the other side as well. If I wanted to find the area of the red region, I could find the area of everything to the right of negative 1.6 and subtract away everything to the right of 2.4. So there's nothing that says that you have to do everything to the left or everything to the right. You can do either or. And one thing that I want to note when we look at this, a positive z-score, this means that we're above the mean, and a negative z-score here means that we are below the mean. And it's really important to notice these sorts of things. This will give you a sense of is something going to be unusual or not? How far away is it from 0? And when we think about 100 and 200 as opposed to 140, well, yes, 100 is below the mean, so it should have a negative z-score. 200 is above the mean, so it should have a positive z-score. Also, it's really tempting to mix up z-scores and area. However, don't. The only thing I can say is just practice. A z-score will correspond to a point along this x-axis. The areas correspond to the filled-in area underneath the curve. And then ultimately, probability is equal to area. So the other way that we can look is, rather than being given a score and finding the z-score and then finding the area, sometimes we can be given an area and we'll have to find the z-score. So women's resting pulse rate is normally distributed with an average of 74 beats per minute and a standard deviation of 12.5 beats per minute. So again, we'll just draw a picture before we think about anything else. So we've got our bell curve. Our mean is going to be 74 beats per minute. Standard deviation is going to be 12.5. And I'm asking, what is P95? Okay, so this is notation that we'll have to remember. So this is the 95th percentile. Meaning, this value is going to be bigger than 95% of the data, but smaller than 0.05%. of the data. So I'm looking for the value, maybe it's out here somewhere, where the area within so this area over here is going to be 0.95, and the area inside here, maybe if I put that in blue, is going to be 0.05. That might be a little bit hard to read. I'll put it above as well. So this is 0.05, and this is going to be 0.95. So what I need to do is I need to find this value here so that it separates 95% of the data from the top 5%. Well, again, we can put this into the standard normal distribution, and then we can use our calculator. So again, here we have a value of 0, but we still want to split this off into the region with 95% of the data and 5% of the data, 0.05. So we can come back to our calculator, and we can do this in two ways, and we'll do both of them. So here, what I'll do is I want the area less than my z-score. I don't know what it is yet, but I want the area less than that to be 0.95. Oops. So 0.95. And the value I get is 1.64. So the z-score here is going to be 1.64. But we did this looking at the area to the left. Maybe we can also do this using the area to the right. So let's try it. So now I want the area bigger than this. Oops. So I want the area bigger than 0.05, and I get the same value, 1.64, which makes sense because if this area is 0.95, this area should be 0.05. It all has to add up to 1. So in the past, we've gone from taking a value to a z-score. Now I have to take that z-score back to the value in here. So this is a pretty simple calculation. If the z-score is going to be x minus the mean divided by the standard deviation, I can solve this for x to get that x is going to be the z-score times our standard deviation plus the mean. Okay, so here's our formula, and we know all of these bits. So this is going to be 1.64 times our standard deviation, which was 12.5, plus our mean, which is 74. And this is the value that we should get. I may have to type this into Google really quick. 1.64 times our standard deviation plus our mean is 94.5. So this value is 94.5. So this is the 95th percentile. To finish off this video, I just want to again remind you that that there are values that are considered significant, and these are essentially the extreme values where the probability that something is bigger than this value is going to be only 5%, and the probability that something is less than this value is going to be 5%. Now, what we just did is we calculated the 95th percentile. So only 5% of values are bigger than this. So in this case, for women's resting pulse rates, anything bigger than, any resting pulse rate greater than 94.5 is going to be considered significant because the probability that that happens is only 5%.